If I didn't give you permission, speak up. So far, we have 9. I think there's 18 in the class. Okay, I got 6:04. I'll just talk about simple things while we get started. So for the oh, and if somebody needs to record, let me know. For the transistors, in your kit, you have an NPN transistor 2N3904. So that's a bipolar transistor. You should have 3 of those in the kit. So those are going to have a pinout similar to this: emitter, base, collector, and then they'll have a flat side. Some of you, I think I sent out some components with actual 2N2222 transistors in them. And so those are in a can. And so to figure out on the can, you've got emitter, base, collector. So the emitter has like a little tab. Like, let's look at this picture here. So the emitter, and then the next one closest to it is the base in the middle. The emitter is closest to the tab. The base is in the middle, and then the collector is on the other side. And then again with the other molded package, generally it's you're looking at the flat side. They usually has like a semicircle shape or a semi-cylinder. So the emitter is going to be on the left, the base in the middle, and the collector on the right. Okay, it's 6:05. I've got 9 participants. I'm going to start. Okay, so we went over the transistor. Okay, so before we get into our lab, first things first, we got to do some background on the next week's lab. Oh, let's see, there's something on the chat. Can you guys hear me?
Yeah.
Do I need to speak louder?
You're fine.
Okay. Ruben, I'm not sure. Is lab 7 due this week is a question. No, this is lab 7 that we're doing right now. So it'll be due like 2 weeks from now. If Moodle is saying that it's due this week, then I need to go edit Moodle. Okay, I'll go make a note to myself and I'll edit Moodle. See, I have a piece of scratch paper here somewhere. Okay. And I'll probably be grading. I haven't graded for a while. I'll grade this weekend or Monday, Tuesday. Usually I say I'm going to grade on Sunday night, and I'm usually talking to my Chinese employers and planning the next week's projects. So anyway. Okay, so I'll update Moodle. So anyway, going in, we got to do some background work first. So this last lab is a design project, and it's really an extension of the lab number 7. We're going to make a common emitter amplifier. It's just you're going to get design specs, and then you're going to have to go figure out. You're going to have to go figure out the component values and then build it and test it and report on how you did. So here's a picture of it here of the circuit. So again, we have a collector resistor, emitter, 2 resistors in the emitter. I'll explain that in a bit, a load, and then input resistors. And we'll learn how to do that today, how to design those input resistors so that you only need one power supply to power it. But there's a number of design specs at the end. Come on, I just had it here. There are a number of design specs at the very end, and so we'll assign those right now. And actually that means what I need to do is open up the teams. Let me see if I can find that. Oh, let's see if I go here, date modified design project. (2018). I'm looking for what we did at the beginning of the semester. I should have pulled it up earlier. With the lab assignments. I'll have to send that out later. I can't, I'm not seeing it right now. Actually, let me look down here. Images and lab notes, see what I got here. Pre-lab notes. No, it's not there. Okay, I've got to go find. Maybe I can find it here. Let's see if this is it. 108. No, that's the schedule. Well, let me open that one. Oh, that's not what I'm looking for. Sorry. Okay, I'll send out an email afterwards, and I'll send out this sheet too, because this sheet is important. This sheet, because we have the analog discovery, we have to modify the specs for the lab. So that lab was written up for use at the university where we have 10-volt supplies. But here we have only 5-volt supply. And so what I'm basically doing in here is I'm basically saying, okay, your spec, like for this one, spec number 1, rather than 8-volt, you'll use 5 volts. And then rather than a 3 volts peak to peak spec, you'll design for 1.5 volt peak to peak. Okay, but you'll still design for a voltage gain of 12 and the resistor load. So this one, for another example, this one had a spec of 9 volts, 6 volts peak to peak, or was it 3.6? 3.6 volts peak to peak. So you'll design for 1.8 and using 5 volts. This one, 1.9. So I basically cut the voltage peak to peak and then assigned it all those 5-volt supply. This last one, CE number 7, has a 5-volt supply. Okay, so there's some notes. Let's see, there's another chat comment here. Oh, Ruben, a quick recap. What we're talking about is the last lab. The last lab we're going to assign. I'll send it out. I couldn't find the team assignments for the kits, but I'll pull that up and then I'll sign that out, and I'll assign one of these specs to each one of the kits. Each one of the teams that has a kit, and then for the last lab, you'll have to go calculate the component values, simulate it, test it, and then like report on, okay, versus my spec, did I meet my design requirements? And did it, how did it perform? And just, that's basically the last lab. So it's a design project, but I'll tweak this a little bit so it doesn't cover up all the specs, and I'll send that out after we talk. Okay, so that's what's going on there. So every team will get a assignment. Let's see what's going on here. Okay. Every team will get an assignment, and you'll have to do the design. I have some design notes on Moodle. Let's see, I think I have those open up here. Let me see if I can find those. Oh, I think I have a PDF over here. Okay, I can send these out too. This is a design example. So actually, let me look at this one here. Okay. So this is actually applies to lab number 7. Okay, so here on this note here, this is on Moodle, I believe. If not, I'll send it out. But this is an example of how to do CE6 spec. So the spec is to have RL equals a 4.7K, V out over VN equals 10, and then VCC equals 10 volts. So we're going to change it to 5 volts. And then the minimum swing, I said on that one, let's try to keep 2 volts peak to peak, but I think that contradicts what I showed earlier. But anyway, 2K, that 12K there. So the way you start these things is you look at your load requirement. Here we need 2 volts peak to peak driving a 4.7K load. And we figure out what kind of current you need to deliver to that load. And then what I generally do is design for 4x or 4 or 3x that load current, and have that coming down the collector, because I want to have enough current coming down to support to bias up my transistor while still being able to deliver current to the load, because it's going to share current to the load. So I'll design for IC equals 4 times IL. So if I have 0.425 needs to be delivered to load, I'll design for IC equals 1.7 milliamps. And that's how I get started. So if I want this thing to oscillate, I've got 5 volts here. Ideally, it'll oscillate around like 2.5 volts, midway between where the emitter voltage and the supply voltage. So what's going to happen is my signal is going to oscillate on the carrier DC offset of the carrier bias voltage or the collector bias voltage. The collector bias voltage. Yeah, it's going to oscillate on that voltage DC offset. So generally I'll design my emitter voltage to be like about 10% of the supply voltage. So I want about 0.5 volts here. And so if I get this to around 2.5 volts here, it's not exactly going to be in the middle. The middle would be like 2.75 volts, but it'll be close enough. And by the way, these designs are iterative processes. So you'll go through the design and simulate it, and it may not be perfect and ideal, and then you'll have to go back and tweak it. I mean, what we'll even find out today is even though we design like for a resistor ratio in the design lab number 7 for 10, generally that gain comes out a little bit less. And so then you got to tweak it. You either got to increase your collector resistance or reduce your emitter resistance. So anyway, these are notes on how to go about doing that. So I said here in this example that I'll design for 5 volts minus 3 volts will be VC. So I'll have VC, the signal actually oscillating on the 3 volt offset, and then divided by 1.7 milliamps. And then that gives me that I need 1.176 ohms or 1.2 k ohms. So my collector resistor is going to be 1.2 k ohms. So this is going to be 5 volts. This is going to be 3 volts. And then if I want a gain of 10 in this example, I have RC divided by RCEA. And so what's happening here is our gain ratio is going to be determined by these 2 resistors here. This one's going to be used to help set up the bias. So if I want a gain of 10, I got 1.2 k ohm here. That means I got 120 ohms here. Okay, that'll give me my gain ratio. But at the same time, I want the emitter to be about 0.5. So if I want 0.5 volts and I got 1.7 milliamps, so 0.5 divided by 1.7 equals, let me do that again, 0.5 divided by 0.0017 equals 294. So almost 300 ohms. And so actually, I think I have an error here. Actually, I want to take that 300 and subtract 120. And then that gives me 174 is what I think. Actually, I think this is an error. I think this should be 174 here. So that the combine of these two is essentially 300. So it'd be actually 180. Yeah, it would actually be 180 here. So I think I actually have an error on this example. But anyway, what's going to happen is from a DC standpoint, these combined resistors is going to set the emitter voltage at about 0.5 volts. And then, but from an AC standpoint, when I have an AC signal coming through, I got a big capacitor here. That's going to short the resistor. And so essentially the gain is going to be determined by RC and REA. But now what we're also going to find is that the load is now in parallel with RC, because essentially 5 volts, this is a DC. That's from a DC standpoint, and I'm sorry, an AC standpoint, that DC supply is like a short circuit, because again, the power supplies have a big capacitor at their output to filter any noise. So these 2 resistors are essentially in parallel. So once you calculate that, you're probably going to have to and test it. You're probably going to find that you're not getting the gain you want. And you're going to probably have to tweak this one up so that the parallel combination of these guys divided by REA will give you a gain of 10. So anyway, there's design notes in the on Moodle. Today we'll actually figure out how to calculate these 2 voltages here. I mean, basically what we got 0.5 volts here, we got 0.7 drop. So we want this voltage here to be about 1.2 volts. And that's for this specific example. But that's just kind of a preview of how you go about doing the design. And there are some other notes. So before next week's lab, try to do the calculations for the specs I assign you. And again, I'll send those out after this evening, after we're off the line. But that's just kind of a preview for lab number 8. And the last thing I want to say about lab number 8 is it's weighted heavier than the other labs. So that's one that you want to get in. If you're getting like an A, but don't hand in lab number 8, you're going to most likely get a B. It'll knock your grade down if you don't hand in the last lab. So that's one you want to make sure you hand in on time to get full credit for it. It's weighted that way. Professor Headley, I actually set up the Moodle page for me, and that's the way he set it up. And again, that's one you don't want to miss. It'll change your grade significantly if you don't hand in lab number 8. Okay, so having said all that, let's go back to lab number 7. Okay, so for lab number 7, when we did our design, we based it, when we did our P-Spice, we had a 10-volt supply, we had a 10K resistor and a 1K resistor and 22K here. So again, for the analog discovery, we have to modify that. So there's 2 things we can do. We can reduce the current going through, or we can reduce the resistor values. So the first thing, I think the easiest thing to do is we'll just keep the resistor values as they are, but rather than designing for 0.5 milliamps, which was what we were doing in our P-Spice, we're going to actually design today for 0.25 milliamps. So that means I got 0.25 milliamps going here. I still have a 10K to 1K. And so my current is going to be 0.25 milliamps divided by the current gain, beta. And so my base current is going to be 1.66 microamps. And then to calculate VBB, I have VBB is equal to 22K ohm here times 1.66 microamps plus 0.7 VBE here, plus 0.25 milliamps, and then it got cut off when I scanned this, times 1K. And so when I did that, I got that VBB should be about 0.986 volts DC. Okay, so that's option 1. I think that's the one we should stick with. Otherwise, I mean, you can go through the calculation again. If you do want to have 0.5 milliamps, you can use a 4.7K and a 470 here. But right now, I mean, the circuit I built is the option 1. So I think we should go with that. And we'll just design this so that the collector voltage is going to be about 2.5 volts, right? So that's how we kind of get to the 0.25 milliamps. We want 5 volts here. We want 2.5 volts here. So across this resistor, we want a 2.5 volt drop. We divide that by 10,000 and we get to 0.25 milliamps. Okay, so that's what's going on there. And now the second half of this is, I got an unstable internet connection apparently. The second half of this is calculating. So we'll revisit this. Right now though, what I'll do is I'll jump to my build. Yeah, I'll jump to the build right now. Okay, so lab, the notes. Okay, so we're in the build portion of lab number 7. An AC signal hooked up. I actually find that actually skipping to step 10 and hooking that up, it's probably the best way to know if your amplifier is working. But anyway, I've got that all set up. But that's not actually what they want us to do in step 9. In step 9, they want us to do a DC sweep. It says basically consider this circuit in figure 1. So I mean, that's what we did. VBB should be a variable voltage source obtained by using the method described in appendix A11.3. Forget that. We're just going to hook it up to WaveGen channel 2. So you got to select channel 1 and turn on channel 2. And then right now I've got it biased at 900 millivolts. And so on my scope, well, you can see it's oscillating around 2.5 volts. So that's kind of midway between the supply and the emitter. You know, it might get a little bit more dynamic range if I brought it up slightly. And we'll actually see that in step number 12, where we check where it clips. But anyway, so anyway, we're using for the VBB at the base, I'm using WaveGen channel 2. I've got a DC setting. And for right now, I mean, you can start with 900 millivolts. That's a good starting spot. And that previous calculations I went over quickly, I think I had like an almost 1 volt. It was like 0.998 volts. But anyway, I found that with the circuit I built today with the 2N2222, 900 millivolts is working good. And then I'll jump back to this. We'll first do the DC portion. So my supply is at 5 volt, my WaveGen's there, and my scope is here. So I'm actually going to turn off the channel 1 WaveGen. And then I'll just look at the scope. So right now, I have nothing at the input, the AC input, but my collector right now is sitting at 2 and 2, just looks like 2.4, just under 2.5 volts. So for step number 9, what it wants us to do is basically step through those voltages and observe this thing turn on, and then calculate what the gain is based on the DC. So in fact, I think I'm going to open up an Excel here. I do a lot of my design work on Excel. Actually, I'll just take a detour really quickly. Where did that go? Hold on. Oh yeah. So this is a design I'm working on today. It's a transformer design. So what I'm looking at here is I'm just evaluating different cores. I'm sorry, the detail, I don't know, maybe this is interesting, maybe not. So these are like ring cores. These are like donut shaped ferrite cores. I'm looking at outer diameter, inner diameter, height, and then I'm looking at its path length and area. And so I want to have a design for a 200 microhenry transformer. And the thing about this transformer, it has to have like a really high voltage breakdown. So I'm just looking at these different core sizes and different number of turns. But anyway, the point here, here's the permeability of the different materials I'm considering. The point here is I do a lot of my design work on spreadsheets like this for the transformers. Okay, but anyway, back to my new sheet. File, new. So I'm going to set this up. I'm going to record VCC is going to be the same. And then I'm going to have, actually, I'll put it over here. I'll have VB. And I'll have VC. And we don't really need to monitor VE. Yeah, that's not really necessary. I mean, you can for kicks, but it's not. I'll record it actually. No, actually, it's going to be, it'll be difficult to record, or I'll have to use a probe to do that. So I'll do VC, and then we need to calculate IC. So IC is basically going to be VCC minus VC, the supply voltage minus the collector voltage divided by the 10K resistor I have in there. Okay. So right now, let's start. I'll just go 0.51, or actually I'll go, right now I have a 0.9. And I'll just take it to 1. I'll go 1.5. And then I'll go 2, 2.5. And then from experience, I know that it's going to pretty much be at saturation. I'll go to 3. So we'll look at those values for VB and see where VC is at. Okay. Oh, I got some new participants, huh? Okay, who needs to record? Who joined? Okay, let me. If anybody else needs to record, speak up. Okay. So anyway, let's go back. I got 2 comments here. Okay. Okay, so go to WaveGen. Minimize this, minimize this. Okay, so let's just go in. So this is a VC and we'll just dial in on WaveGen the different voltages. So first we'll just put it at 0.5. Okay, and let's see what's going on at the scope. Okay, so it's pulled up. It's pretty much off. So my VCC right now, let's see if I put this up here, it'll tell me where I'm at. This is on, when you use these markers, by the way, these cursors, you got to select, if you haven't figured that out, you got to select channel 1 and channel 2. So this says I'm at 4.9 volts. Actually, I'm going to even put in something small and just see if that's as high as it goes. I'm going to say 0.1 volt. And let's just see where that's at. Oh, come on. Scope. Okay, we can't see it, so it's essentially behind there. So that's the maximum. So when the oh, maybe I didn't get that in there. Let me try that again. 0.1 volt. Or I'll just do 100. Let's see what happens now. Scope. Okay, so it did go up slightly. So yeah, when the transistor's turned off, you're essentially going to be up there. Okay, but anyway, I'll put that back at 0.1 volt or 0.5 volts. Okay, and so that tells me my transistor's barely turned on. Let me get a pin. Scratch down some notes real quick. So I got 4.96. And then I'll go to 900 millivolts. It's starting to turn on. Actually, I think I'm going to add a 0.75. Okay, so I'm going to go back. Well, okay. Yeah, let me just do it 0.75. Okay, so when my collector is at 0.75, this guy's at 3.5 volts. When my base is at 0.75, I'm at 3.59 at the collector. And then I'm going to do 0.9 again, because that's where I think my sweet spot is. So that's got me at 2.4, I think. $2.43. Okay. So the next one. At 1 volt, I'm at 1.62, 1.5. I have a feeling I'm almost going to be in saturation. At 1.5, I'm at 1.47. And then at 2, I'm pretty much the same. So 1.47 is essentially where I'm saturating at. I'm going to have one more there in the middle then. I'm going to do 1.25 and add that one. Oh, that didn't make much difference. I'm going to do 1.1. Add that one. So we have a really fast transition or forward active region. Okay, so I'm going to add this one in here. Okay, so at 1.1, I've got C2 at 1.47. Okay, so now I'm going to put that in my spreadsheet. Okay. Oh, and I also had a 0.75. Okay, so this is going to be 5 all the way down. And then I've got 4.96. So that's essentially the supply voltage. And then here I'm at 3.59, 2.43, 1.47, 1.1. I was at 1.62. Oh wait, I have that confused. I had a yeah, I didn't write that down. I didn't record that well. Because this is, I forget what I did. I'm just going to get rid of that one. Let me just see once again with 1 volt. I think I have that recorded right. Okay, actually 1.1, I have 1.47. Okay, let me adjust that. And then at 1.5, I have 1.47. That's I'm already in saturation. Let me just check that to make sure. I'll just put this at 2. Let's see if it moves. Oh, this is my saturation region here. I'm confusing myself. Okay, I'm moving the wrong cursor. Okay, now I've totally confused myself. C2 is here. Okay, that's my saturation there. Okay, I recorded some bad data. Okay, so when I'm at C2 is at 29. Actually, I'm confused because this is 0. This is 1. It looks like it's at 0.5. What's going on here? Put 1 down there, bring 2 up here. Yeah, that's bizarre. 510 millivolts and then jumps to. Okay, I believe that. I think that's my saturation with 2 volts. Let me put that one in there. So I've got it right now at 2 and I'm at 510. And then let me repeat 1.5. Huh. Okay, let's see what's going on here. If I go to 1.5 is essentially at 510. So if I go 1.1. Okay, so apparently 1.5 in saturation too. And this says, oh, come on. This is not right. It's not 18. What's going on with my, oh, maybe it's all compressed. Oh, crap. Okay. Dang it. Okay, so let me see where I'm at. I'm confusing the heck out of myself. 1.1, I got 818 millivolts. And then I gotta check one more time, 1.5. Okay, 1.5, I'm at 529. And then I was at 510 at 2. Okay, I'm just going to record those and go with that. So I think 500 were pretty much at saturation. Okay, 0.51. So here at 1.5, I was at 529. And then 1.1, I was at 818. Okay, so now my current is going to be equals C3 minus D3 slash 10,000. Okay. These have to be millivolts. Oh, I can get this. Okay. So these are in amps. These are in volts. Okay, so this is saying that when I have 1.1, I've basically got like 0.4 milliamps. Now, again, we scaled this down because we have the 5-volt supply. So our sweet spot is when we have like in the lab write-up that and what we simulated in Moodle, I'm sorry, in PSpice, we wanted 0.5 amps. Here, what we're designing for today is 0.25 amps. So again, 0.9 seems to be our sweet spot. Okay, so the last part of this step 9 is to figure out the gain. So I want you to take a delta. So I'll just say G is equal to, and so I'm going to take a delta of VC. So I'll take it at 0.75 and 9, or I'll take it at 0.75 and 1.1. So I'll say D4 minus D6. I'll put parentheses around that. Oops. Come on. And then I'll say slash, and then B4 minus B6. Oh, okay. That's my gain. I don't need the G there. Did I just erase that? Oh my gosh. Where's my back? Okay, let's see what I got. So that says I have a gain of 7.92. So again, it's negative, which is fine because it's basically an inverting amplifier. But that's we have a resistor ratio of 10. So we're not performing really good. You know, it's just like about 8. So it is what it is. You know, these transistors, you know, this is a very old transistor. Newer transistors, I think you'll get better current gain out of. But this one's just giving me like apparently 792. But what's important is that when I do that calculation, I pull, okay, so here I'm in cutoff, because I'm basically at the supply voltage. And then here I've basically bottomed out. I'm at saturation when I get to about 0.5 volts. So when I do that calculation, I just pull values that are within the forward active region here, where it's transitioning from 5 volts to 0.5 volts. Okay, I think that's enough for step number 9. So step number 10, in the lab instructions, we hook a capacitor, and that capacitor takes us directly to the base. Let me close this right now. Let's go back up. So this is a detail that you just got to really pay attention to, because like in my students, you know, when I do the lab in class, people always try to connect the signal in here. You're connecting it directly to the base. So the diagram for step 10 is basically put a signal source and put a big capacitor. Today I'm using like 22 microfarads, but in your kit you have stuff. Let's see, we have capacitors ranging from 1 microfarad to 220. You know, any one of those would work. So just find a bigger one. The 0.1 might be a little bit limited. We're putting in a 10 kilohertz signal, so the impedance should be pretty low on 1 microfarad or something bigger. But anyway, just note this. This connects directly to the base of the transistor. So it doesn't connect to the resistor, the 22K resistor. It connects basically in parallel with that. Okay. So anyway, back to my wave gen. So let's turn that back on. Let's get this all set up again. Supplies, wave gen. Okay, so I had my sweet spot was like 0.9 here. And then I'm going to run this one here. And then here I got my signals. Okay, so this thing's riding at about 2.4 volts as a mid spot. And let's check my gain. So I got my cursor here. Oops. Let's bring this down. 2 always tracks the first one. So I basically have a peak-to-peak voltage on my output at my collector of, okay, it's the minimum is essentially 1.49, and then the maximum is 3.32, and then I've got a delta of 1.83. Now my input signal is going from 100 millivolts to minus 100 millivolts, so it's 200 millivolts peak to peak. So here, what my gain is, I can calculate. I've got 1.83 divided by 1.83 volts peak to peak divided by 0.2 volts peak to peak. That indicates that my gain here is actually 9.15, a ratio of 9.15. So it's closer to 10. It's closer to the desired values. And, you know, in your design project at the end, what you're going to end up doing is you're going to end up tweaking your resistor values. You'll build it first, or you'll simulate it first. And then, you know, it's an iterative process. You'll see how it performs, and then you'll have to figure out, okay, what do I change? Now, there's 2 things you can change that are very obvious. You can increase the collector resistor, or you can decrease the emitter resistor and just increase that ratio slightly to get it if you want a gain of exactly 10. Other thing to note though is when you do that, when you do your design project, is there are tolerances in all those. So it may say you need a gain of 12 plus or minus 10%. And so 12 times 0.9, that's 10.8. So like if you're only getting a gain ratio of 11, you're still within your spec. That's just a detail. Anyway, let's just review a few things going on here. So wave gen, I've got it set up for 100 millivolts peak. So that's 200 millivolts peak to peak, 10 kilohertz. Right now I've got a sine wave going through it. I'm actually going to change it to a triangle right now because step 12, I guess it is, we see where things start clipping. So I've got my timing right now at 10 microseconds per division. It's a 10 kilohertz signal. I mean, we can spread out a little bit if we go to 50. I've got the channel 2 where my output signal is at 1 volt per division. I've got my input at 500 millivolts per division. So I've got those different. But anyway, you can organize your display as you see fit. Okay, so that's step 10. We've got that running. We checked our gain. Step 11, it says, for the gain measurement conditions of the previous step, sketch the waveform at the collector. On the sketch, label the DC component. You don't have to make a sketch. Just do a screenshot and then label on your plot. You can make a line through it or just put a label and say, the collector, DC collector voltage is in my case, 2.4 volts. In step 10, though, it actually asks you to record the base voltage. So in my case, the base voltage is here. Well, this is actually VBB. You can measure on the other side of the 22K ohm resistor and figure out what that voltage is there. And then you got an AC voltage of 0.2 volts peak to peak. And then we've got our collector voltage here. And we have its DC and its AC peak to peak. So you record all that in 10. So in step 11, basically you're just taking a screenshot here and you're annotating it with the VC value and the VB values and so forth. Okay, so that's step 10, that's step 11. So step 12, it says increase the AC signal input until VC shows clipping at both peaks. So we're going to figure out what the dynamic range is of this thing. So I'll go back to wave gen. So right now I have 900 millivolts. So let's just try 1.5. That'll give me, oh, I'm sorry. I don't want to change that one. Duh. Okay, let me get that back. 900 millivolts here. I want to change this to, let's try 200 millivolts. Actually, I can probably select that. Oops. Okay, so we go to the scope. Oh, no clipping. Okay, that's good. Let's go. We're getting close though, because here's the 5 volt supply, and then we're getting down. Oh, we're going to clip very soon because the emitter is sitting at 0.5 volts. So if I just take this up a smidgen, if I go to 250 millivolts, I think we'll see clipping. Okay, let me turn off that channel. So we see clipping in the bottom here. The top is still looking pretty good. So I'm going to increase it up even more and see where it clips on the top. I'm not sure if it makes it all the way to VCC. Oh, man. Okay. Okay, let's do this. Here we'll see some clipping. Okay, so basically, I didn't think, I thought it would clip sooner. It's basically clipping between VCC and then the emitter voltage, which is 0.5 volts. So if I set my cursors, my like maximum dynamic range is going to be like 4.5 volts. I'm gonna back off a little bit and see if I can find. I think I'm gonna go like 240. Let's see what that looks like. Okay, so it's just beginning to clip at the bottom, I believe. Yeah, now I can improve that a little bit because I can go and now tweak this guy. I'm gonna go to 9.5 millivolts and see if I can raise that up a bit. Oh, I went the wrong direction. I had to back off actually. I should go to 850. Okay, so now I can get a little more dynamic range out of it. By the way, I'm just playing now. This isn't necessarily what you need to do in your lab. So let me put this at 360 or 260 rather. That's looking pretty sweet. I'm oscillating right now a little bit over 2.5. That's looking pretty good. I can see if I can get a little bit more out of that. Okay, I think I'm just about to clip at the bottom. I'm going to go up to I'll just go up to 300. I think we'll see a clip. Okay, it's clipping, but just barely. So anyway, what I ended up doing there was I had this at 900 before. I reduced it to 850. And what happened is my DC, okay, so as VB goes up, as VB goes up, VC goes down. And as VB goes down, VC goes up. So it's an inverse relationship. And so I reduced VB slightly and it moved my collector voltage, which is where my signal's oscillating around. Okay, so that's essentially step 10. Just figure out where it clips, what's the dynamic range. It says here, make sure your oscilloscope is in DC coupling. I think the analog discoveries are always in DC coupling. Okay, I think we pretty much did that. It says draw a sketch, just take a screenshot. Okay, now the last part is you're right now we're using the second supply right here to power up the base, to bias the base. For the last step, we're going to use a resistor divider. And so we have to calculate those resistors. So we have to set up 2 equations and 2 unknowns. And I think I have that example here. Okay, so our biasing options for this one here. Okay, so I did this, past labs when we were teaching in Moodle. So I think when I did it in the past, I calculated that VBE is 0.7, VB should be 0.95 volts. Okay, and this will work for us. We had at 0.9, so let's just see what 0.95 looks like real quick. I just go to 0.95. Rather than redoing the calculations, we'll just go with what's here. Okay, and I probably got to back this off to 100 millivolts again. Okay, let's see what's going on. Okay, so that still works for us. I can turn on the other channel. Okay, it's just though now it's oscillating around 2 volts. So it's not ideal. It's not going to give us the maximum swing. But let's just see if we can set up this bias condition. So I'll go to that calculation. So the way we set it up is I basically determined that with 0.25 milliamps going through the emitter, the collector current is essentially the emitter current. And I got a 1 k ohm resistor there. My VB is going to be 0.7, which is my VBE plus 0.25 times 1K gives me 0.95 volts. So the first equation I'll set up is that, well, actually I have it labeled here as the second one. And then the other data point we have is our RN is going to be 22 K ohms. So rather than have that 22 K ohm resistor, we're going to replace it with 2 resistors here. And there again, this is a DC supply. So these resistors from an AC standpoint are in parallel. So the impedance is essentially going to be the parallel combination of those resistors. Looking into the collector, the base, that's a very high impedance. So the resistor of that base isn't of any real consequence in this circuit. So anyway, we want 0.95 volts here. So we want to calculate a resistor divider. So we set up two equations and two unknowns. So we got 22K is equal to R1, R2 divided by R1 plus R2. And then we have VB is equal to 0.95, which is equal to 5 volts times R2 over R1 plus R2. So now we can do like some math here. We can bring the 5 volts over here. We can go 0.95 divided by 5 volts, and then bring the R1, R2 over there is equal to R2. So I'm just manipulating this equation here. And that gave me 0.19 R1 plus 0.19 R2 is equal to, oh, I think I have that cut off here. Let me just write that out. I have that cut off in this example. It's 0.19 R1 plus R plus 19 R2 is equal to R2. And then I get 0.19 R1 is equal to 1 minus 0.19, which is equal to 0.81 R2. The R2 is cut off here and here. So I get R1 is equal to 0.46 R2. And then I plug that back into this equation here. So first I use the voltage divider equation to solve for R1. And then I plug that into this equation here. I have 22K times 4.26 R2 plus R2 with 4.26 R2 times R2 in the numerator. So I multiply that in, and then I multiply this denominator by here. I get 22K times 2.46 R2 plus 22K R2 is equal to 4.26 R2 times R2. I can divide out the R2s, and I get, I basically get 115.7 R2 is equal to 4.26 R2 squared. And I basically get, if I divide that by 4.26, I get 27.1K is equal to R2. And then if I multiply that times 4.26, I get R. So hopefully you can follow that math. Again, you're setting up two equations, two unknown, one based on a voltage divider for the base, and one based on the input impedance. Okay, so to get these values, I actually have 120K resistor. But in your kit, I think you have a 20K, which is red, black, orange, and you have 100K, which is brown, black, yellow. So you can put two of those in series to get 120K. So we're basically rounding this 115 up to 120K. And then here I have a 22K, and I said 20K and 6.8K. Yeah, you don't have 22K. I have a 22K in my hand here, but here you have 4.7K. And do you have a 6.8? Oh, you have a 6.8 and a 20K. So you can use a 6.8 and a 20K to get that value. And that'll give you about what I calculate here, about 0.91 volts. So that should be good. Okay, so now let me see if I can hook that up and just demonstrate that. So I'm going to pull out the 22K resistor and try to set up that bias. Actually, I'm going to use my 22K resistor in series with a that's going to go to ground from the base, and it's going to be in series with a 4.7K. Okay, 4.7K. Oh, I thought I pulled it earlier. I got a 120K. Oh, here it is. Boy, the lighting in my room is so poor. Can't see them. Let's see. Okay, 4.7 and 120. Okay, so here's 4.7. So I got 4.7 in series with 22K. And that's going to give me about 126. And then I got another resistor now going from the base. Come on, go in there. Okay. And then you're going up to VCC. Right over here. Okay. Did I lose some gain here? Okay, there it goes. So I was able to get that. So I put those two resistors in now. And so right now my midpoint, let's see. I got 1.8 again. I got 0.2 volts peak to peak in. So I still got about the same gain. And now my midpoint is going to be 3.11 minus 1 point. Well, basically it's going to be 1.3 plus 0.9. So my midpoint right now is at about 2.2 volts. Okay, so 0.9, I got 0.9. I basically divide this in half and added it to this marker here. Yeah. Marker number, yeah, this one here. This plus 0.9 gives me 2.2. Okay, so anyway, this last one, calculate the value, show the math, and show a screenshot that you got it going. And then again on this lab write-up, oh, and then measure the gain. So in this case, again, it's 1.8 volts divided by 0.2 volts. So that gives me a gain of 1.8 times, essentially times 5. It gives me a gain of 9. And I've got 2.2 volts. It says measure IC. So I got 2.5 volts. I'm sorry, I got 5 volts. 5 minus 2.2, which is my VC, divided by 10,000. So that says my IC current is 0.28 milliamps. Okay, so again, to measure the current going through the collector, it's VC minus, I'm sorry, it's VCC, the supply voltage minus VC divided by the collector resistor. Okay, so we're basically done. Let's see. So yeah, show the math for the resistors that you calculate, and then just do a screenshot, and then it says measure IC and the gain. So I think we're basically done with this today. Okay, any questions? I'll send out the assignments and that marked up spec sheet later this evening after I have dinner, and that'll be for lab number 8. And hopefully for next week you can calculate it if and perhaps even try to simulate it. And then if I'll do an example simulation and I'll go over the calculations again. And that, but if you make the attempt to calculate it first and simulate it, you can ask questions next week and I can help you get through that. And then you'll be ready to build. Okay. Let's see. No questions in the chat. I'm about ready to shut this down. And any other comments or anything? You guys good for tonight?
Yeah, we're good.
Okay, I'm going to end it. Good luck, everybody, and I'll see you next week.
Thanks, Professor. Have a good one.
Okay, bye.